All right, let's try that again. Yep, here we go. We've been talking before the test about forces. In particular, we were talking about Newton's laws for forces. Newton's first law, put your phone away, Brees. Newton's first law says, it's often called the law of inertia. Basically, it says this: if you're accelerating, the net force on you can't be zero. The way I phrased that last year was I said there must be an unbalanced force on you. This year I'll often say the net force can't be zero. If you're not accelerating, and remember, not accelerating means either at rest or straight line steady speed, then the net force on you must be zero. I think last year I said the forces must be balanced. That's Newton's first. That helps us draw our free body diagrams quite often because we will be able to reason our way to missing forces. Newton's second is F equals ma. That's a lie. That's what I taught you last year. It's really F net, the net force, equals ma. Now, what that meant last year, the way I phrased it, my version of Newton's second law is winner minus loser equals F net. Winner minus loser equals ma. And what I was really saying last year, Alec, by going winner minus loser, I was really saying total up all the forces. Now this year, we might have forces in more than one direction and at angles. Did I say angles? That will be a job for components, okay? But it's still going to be building on our Physics 11 method. We'll just maybe have two different, maybe a vertical and maybe a horizontal winner minus loser equation. Newton's third is the action-reaction law, which I've phrased as forces come in pairs. If I push on something with 5 newtons, the object pushes back on me with 5 newtons. That one we'll use both in our free body diagrams, but also to figure out the value of missing forces. Oh, I know how big that force has to be because I know how big the initiation contact force is. It's the same magnitude, just opposite direction. We talked a little bit about weight. Weight. We said weight is mg, the force of gravity. And I introduced you to this concept of gravitational field strength, symbolized by a lowercase g. You can write that down if you want to, but we'll do that later. And that's 9.8 on the Earth. The reason an object in free fall accelerates at 9.8 meters per second squared is because the force of the Earth on it is 9.8 newtons on every kilogram. And we did show that newtons per kilogram was equivalent to an acceleration, so it must be the same as meters per second squared. And that we're going to branch off a lot more when we do rocket science. We'll calculate the gravitational field strength of the moon. We'll calculate the gravitational field strength of Mars. We'll calculate the gravitational field strength of the Earth, but not on the surface. What if you're 5,000 kilometers up? We can do all of that. All right, so there's my jogging your memory. Example 4 says, find the unbalanced force or the resultant force, or the word I'm going to use more often this year is the net force. In each case, include direction. Let's go north, south, east, west. We could also go up, down, left, right. I don't know whether we're looking at these from above or from the side. So let's decide that we're looking at them from above. What's the net force in A? Magnitude and direction. Don't overcomplicate it. Kiana. Units. Direction. Wow, you guys are laughing because I botched that. I told you, this is why I do the compass rose. I just clued in what was going on there. My brain is losing power as well, apparently. How about that? Is that better? East, you say, not south? So 2 newtons. I put an at symbol for the east because if it's north, then it would go 2NN, which is confusing. So after the at, I know it's a direction. In front of the at, I know it's newtons. What's the net force in B? Thank you. What's the net force in B? Huh? I may have to plug in here, but we'll see if I can go without because this has worked so well. 3 point, guys, quiet please, thank you. 3.7 F net would be 3.7 newtons, and a direction would be south. Good. What's the net force in C? Magnitude and direction. 1 Newton north, 1 Newton north. Yep. Now you may be saying to yourself, Mr. Dewick, why didn't you put anything at angles? Did I say angles, Alec? That's going to be a job for? I'm going to turn them all into questions like this. Okay? What's the net force in D? Josh, my friend, what's the net force, magnitude, and direction in D? Eight newtons east? I disagree. 5 newtons east. I'll agree with that. This is what most of our diagrams are going to end up looking like. We're going to have forces in the up-down, north-south direction, and forces in the east-west direction. What's the net force in the north-south direction? 0. So what can you tell me about this object's motion in the north-south direction? Is it accelerating? So it could be going at a constant speed, north or south, or it's at rest. Okay? What's the net force in E then? Horizontally or east-west? Connor L.
7.
Direction?
West.
Which way must this object be accelerating? Must be accelerating to the west. Okay? Remember the tricycle demonstration that we did. The what? Pierce, you missed a good one. Which way must object F be accelerating? Direction. Okay, must be south or down. Has to be. How would I calculate the net force mathematically? Well, I think the net force would be the bigger one minus the smaller one. I'll put it in brackets just to say that's the force. The units would be newtons at south. Those of you that had me last year, you may see the hints of winner minus loser. That's really what we did last year. And that's why I always said, who's the winning force? And we could usually figure out who the winning force was just because we knew how stuff moved. To solve force problems, we're going to draw a free body diagram, an FBD. We're going to draw one arrow for each force that acts on the object. And then this is really important. We're never going to put F net on a free body diagram. F net does not appear on our free body diagram, Brisa. F net, it's the combination, it's the vector sum of all the forces acting on it. But you'll notice, for example, in E, the 7 newtons does not appear on the diagram itself. And that's a common mistake kids will make as diagrams get more and more complicated. Or if they give you the net force and they're wanting you to work your way backwards, you'll be tempted to put F net on the diagram itself. Do not. We label all the arrows. We put the tail of the arrow whenever possible at the center of the object or close to the center of the object. My friend who typed this up often labels acceleration and velocity vectors, and he labels them differently, so he'll do acceleration as a little squiggly line and things. I tend to keep my free body diagrams fairly pure. I put forces and nothing else on them, usually. Then, we use the free body diagram to write an algebraic net force equation like example 4F. And we use this net force equation. How are we going to generate this net force equation? We're going to use a tug-of-war analogy. We're going to imagine that these forces are tugging at each other in the same direction or at opposite directions. We're going to ask ourselves which force is winning, and then we're going to use winner minus loser equals F net. And Pierce, this will help us to avoid having to decide ahead of time which way is positive, which way is negative. So in this unit, I'm going to tell you right now Down will not always be negative anymore. In fact, when we plug in a 9.8 for an acceleration due to gravity in this unit, we're going to ditch the negative. We'll take care of the negative in our reference frame when we decide to let positive be whichever is most mathematically convenient, not whichever is the convention. As an example, a 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. A says draw an FBD. What's an FBD? A free body diagram. What are we going to do? We're going to represent the rock with a dot right there. That's the rock. Put a little dot there. Then we're going to list the forces acting on this rock. And I always say to myself, what are the forces acting on this rock? Get the obvious one. Which is the obvious one? Okay, so I always label that first because I want to go systematically. And which way is gravity acting? So I'm going to draw an arrow pointing down. And I'll call that FG, force of gravity. So far so good, Connor? Yeah. Other Connor? Wow, 3 of you in one glance is a little weird. Are there any other forces acting on this rock? I know there have to be, because if there were no other forces, it would be in free fall. And if it was in free fall, what would the acceleration be? Not 3. So I know there must be other forces. There is another force up. Which way is this rock accelerating according to the question? You know what? Right now, since you're all yawning, underline the word upwards. That's important. I'm going to ask you the same question. I'm going to phrase it differently, but I want the same answer. Which way is the longest arrow winning force going to be pointing? Because it's accelerating up, I know that has to be the winning force. So I'll exaggerate it, making it way longer so it catches my eye. Then the next question is, what force is that? What's causing it to accelerate up? Well, it's the rope or the cable, but we gave that force a special name. What did we call that force last year? Tension. And that's it. Those are the forces acting on the object. Mr. Dewick, isn't there a normal force? Is it sitting on a surface? No normal force. We'll talk about that another day. So A says, draw a free body diagram. Done. B says, compare the forces. We actually did that in our free body diagram. Who's winning? Okay. C says, write a net force equation. So if I was writing a net force equation, it would look like this. Tension minus winner minus loser. Tension minus mg. Mg is the force of gravity. It's the weight. I plugged that in for Fg. Tension minus mg winner minus loser equals net force. But what did I say F net was as an equation? F equals ma. Okay. You stay on that page. I'll go back here. This is exactly what we did. Who's the biggest force minus who's the smallest force, and that equals the net force. What did D want me to find? How would I get the T by itself? How will I move this minus mg to the other side? Here you go. Tension is going to be ma plus mg. Let's see if we can get this. Did they give me the mass? I've scrolled down. What was the mass? Is it in the question somewhere? Did they give me the mass in kilograms? No. What did they give me? Sorry? Weight. Force of gravity. mg. So the mg is 2,000. Did they give me the acceleration A in this question? What?
3.
Okay, I'll put a 3 here. If I know the weight, if I know the mg, how can I figure out the mass? Who remembers from last year? Emily. That's the mass. What's the tension? I mean, you could calculate the mass, but if I'm going to type that into my calculator, why don't I just put that in the equation, then there's no rounding off. 2,000 divided by 9.8 times 3 plus 2,000. I get a tension in the cable of 2,612. I'll go 2610. I'll go to 3 sig figs. Newtons. Okay. So here's my analog. Here's my rock. We're accelerating up at 3 meters per second squared. The tension in this rope is 2,610 newtons. Here's our question. Example 6. Is it correct to say that if the rock is moving upwards, the string tension must always be larger than the weight of the rock? The string tension must always be larger than gravity? Is that correct? Hey, once again, we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. So this is our thought question. If the rock is moving upwards, does the tension have to be bigger than mg? Who says true? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nice vote. No? 11? Who says false? 1, 2, 3, 4, 5. Did you vote? True or false? You said true? Did you vote, Pauline? So if we're going to go false. Okay. I think 7. Convince me. Attack or defend. Convince me that you're right. The false people, can you give me a situation where the rock could be moving upwards and the tension was not larger than mg, than the weight? I mean, you voted false. You must have had a reason. I'll help you out just to give you some confidence. That's the correct answer. If you're at a constant speed, what's your acceleration? Okay? You okay with that? So then my equation would look like this. Tension equals ma plus mg. Still, who's winning? Tension. Yes? What's A if we're moving at a constant speed, Justin? So that whole term would cancel. And I'd get this. Tension equals mg. In that situation, is tension greater than mg? No, they're bang the same. So false. It doesn't always have to be bigger. Okay, have I convinced you? By the way, that's a lovely proof. Almost no English. In fact, if you just said A equals 0 without writing constant speed, I'd get it. And then some nice math lines, algebra, generic proof. That would be an idea of a good using principles of physics right to explain testy sort of a question, except I'm not going to ask that one because I just did it with you. Okay. For a rock moving upwards, same situation, is it ever possible for tension to be less than gravity? Less than the weight. Ooh. I've just shown that it's possible for it to be equal, and therefore not greater than. Can it ever be less than? Once again, we're going to vote. Once again, all of you are going to vote. If you're not sure, just don't hold your hand up very high, but you have to vote. So who says, yeah, it can be less than? 1, 2, 3, 4. Who says, can't be less than, Mr. Dewitt, there's a rope. I'm going to show you a picture. No, I'm going to, do an example, and I'll let you decide if you want to change your vote. Here is my analog. Yes? Here is my rock. See the tension? Yes? Watch closely. Is it ever possible for the rock to be moving upwards but have tension be less than gravity? Yes or no? Connor nodded. Why? What did you notice when I gave this a big jerk? When I yanked it, what did you notice happened to the rope itself, to the tension? And as a number, what would it be exactly for a split second? 0. Yes? Okay. If you give the rock a big jerk, if the rock is in free fall for a split second, it's still moving up. It's accelerating down, but it's still moving up. And you saw the rope go slack. Yes? That little bit of physics right there, really tough to analyze. So, yes? If you jerk on the rope, it goes slack and tension is 0. Well, you know what? Let's write it in physics. And T equals 0, which is definitely less than mg. We're not going to study that situation in terms of writing an equation for it. We can handle it. So far, so good. Next page. I got to go a little technical here. Every so often, this is when I have to be fussy if I ever write technical comment. And remember, nice try, Josh, we said that this lesson photocopied strangely, if you're wondering. So whenever we turn the page, for this one lesson, it photocopied the pages in opposite order. So find where it says technical comment. Okay, here we go. So, supposing we had this mass accelerating downwards. Supposing we had this mass accelerating downwards, we have two options. We could always let down be negative, but then you end up with equations where you have a whole bunch of minuses and yuckiness that can go. So I'm not going to do it this way. Instead, I'm going to take the direction of the acceleration or the larger force as positive. Winner. For the rock, since it's accelerating down, the net force is down, and you would have an equation who's winning. Gravity minus tension equals ma. And we're going to do it that way because we're going to start to look at situations where we have some objects accelerating right, which is positive, while some objects are accelerating down, which is negative. What's the correct sign convention? You know what? Let's let the correct sign convention be whatever makes the math the easiest. I did a tricycle demonstration with you last class to convince you of the usefulness of a free body diagram. What's your homework? Number 1. Find where that is. Yep. Number 2. 3. 3 is an algebraic question. In Physics 11, I tended... Find it now? Yeah, find it now? 3 is an algebraic question. In Physics 11, I tended to avoid algebraic questions. In Physics 12, you can expect for the rest of the year on most of your tests as a multiple choice question, one where I don't give you numbers, where I do something purely algebraically. I'll give you a situation and I'll say, okay, what if f is twice as big? Now what? Or what if m is 3m? Now what? Five is good. 6 is good. 7 is good. I think I skipped 4, yes. Blah, blah, blah. 9 is good. I skipped 8. 11 is good. Be with you right in a second. 12 is good. 13 is good. These are conceptual questions. 14 and 15 is good. These are conceptual questions.